If x is approaching 2, the limit of our line is 1. So the indication of the dependent variable is counted also by the independent variable. Yes or no? As the independent variable is approaching a point, the dependent variable is also approaching its limit. Yes or no? Now, I believe you ask.
The first rule, so I'm saying you have a function that maps A to B like this. Now, I said function is a rule that assigns elements from this particular set to this particular set. Now, the rule, the first one, we have just two of them. The first rule is that given any x an element of A, this particular set, there exists y an element of B, this other set, such that the other pairs x comma y is an element of the solution set f of f. Now, this is what I'm saying. Now, I know I just used another term now, which is the term solution set. I will explain what it means very well. So that is just the same thing as writing y being equal to f of x. I'm sure you must have seen something like this before. So this is just you saying that anytime you have an input or any first coordinate element, then there must exist or there exists a y an element of B. It means that for every first coordinate element, there's a second coordinate element that it relates to. So what that means is that in no case should we have any element in this particular set. In no case should we have any element in this set that does not have an image. So in a case where maybe 3 is not mapping to anything, then that is not a function. Why? Because all the elements in the first set or the domain set must have an image. So that is y is equal to f of x. So for every input, there's an output. And when we go further into the concept of function or relation, you get to learn that this is called the independent variable because it does not need anything to have meaning. And this is the dependent variable because it depends on this. So for example, if I write y is equal to 2x plus 1, now x can be 1, x can be 2, x can be anything. So let's say x is any integer between 3 and minus 1. Any integer between 3 and minus 1. So x can be minus 1 itself, it can be 0, it can be 1, it can be 2, it can be 3. So I said any integer. Now, when x is minus 1, y will be minus 1. I'm sure you understand how that happened. So if you put minus 1 here, that will be minus 2 plus 1 minus 1. When x is 0, y will be 1. When x is 1, y will be 3. Like that. So y depends on x. So y is called the dependent variable and x is called the independent variable. Now, I used the word solution set. Now, anytime you hear the word solution set, f of a function f, it means a set that actually, it is a set that brings together all the other pairs of your relation. So, something like this. So, where you have y to being a function of x operating there, and x is an element of A, and y is an element of B. So I said function is a rule. So your y equal to f of x depends on wherever you are given. It depends on wherever you are given. A very good example of what I'm saying. So I said I'm about to give you two rules, and I've given you one already. And the first is that given any x an element of A, the first set, there exists a y an element of B, the second set, such that this other pairs is an element of the solution set of F. So in short, all this grammar is just to tell you that for every input, you must have an output. Simple as ABC. For every input, you must have an output. And I'm still going to give you an example on that, such that you understand really well. The second rule is that for any x comma y1 and x comma y2, which are in the solution set. I already defined what solution set is. Is the set of the other pairs that brings together all the other pairs in that relation, all of them. Now you have x comma y1 and x comma y2 in the solution set. So it means that in this case, let's say you have 1 comma 3 and you have the same 1 comma, let's say 5. So what do you think is happening here? This is a case of one to many, right? It means that you have 1 in the domain mapping to 2 elements in the codomain 3 and 5, and we already said it, that is not allowed for a function. That is not allowed for a function. Now, in what case will this rule make sense? Now let us go. So I said if you have x comma y1 and x comma y2, which are elements of the solution set, then it implies if at all this guy is in the solution set, then it only means one and one thing. And what it means is that y1 is the same thing as y2. Now, for some of you, you will find this somehow abstract. The things I've been talking about since morning. Why is function is abstract? I thought function is a very simple concept. Function is actually very simple. That is why I need you to work with me carefully so that you will not miss anything. Now, it only means that y1 must and should be equal to y2. That is, if you say y1 is equal to f of x and y2 is equal to f of x, the same f of x. So you are telling me that 3 gives you a function of 1 and maybe 2 gives you a function of the same 1. Then, so they are saying if y1 is equal to f of x and y2 is equal to f of x are true, if they are true, then y1 is equal to y2. So it means it gives no chance for one to many. It gives no chance for one to many. So it means so that means that our definition of function lies on 2 principles. The first principle, the summary of the 2 rules I just gave you now, is that all elements in the domain, must have image. Then number 2, the elements stated in I above, in the first principle above, must have only one image. So they are not permitted to have more than one image. Do you understand? And that's it. They are not permitted to have more than one image. They can have only one image. They can't have more than one. And that solves that. Now, I said that given any x an element of A, there exists y an element of B such that x comma y is an element of the solution set, giving you an insight to all elements in the domain having images. Do you understand? And the second one tells you that the image must only be one. So no element in the domain is permitted to map to more than one element in the codomain. So let me quickly give you examples to make this really easy for you. Now, let's say I have a rule that maps. So let's say the first rule I want to consider is y being equal to 2x plus 3. If y is equal to 2x plus 3, then I want to define a function here. Now, let's say our x is between maybe 1. Don't worry, let me give you this. So you have a function that maps A to B. It maps A to B. And in this case, x is an element of A and y is an element of B. Now, let's say the elements in A are 1, 2, 3, 4. And let's say the elements in B. In fact, from this definition, this element in A, when x is 1, you know that y will be 5. When x is 2, and you put it here, y will be 7. Y will be 7. When x is 3 and you put 3 here, then y will be 9. when x is 4 and you put 4 here, then y will be 11. Now let's say I still have another element here, maybe 13. Now from this rule, this is the rule. So it will be rule that we're working with. We said function is a rule that assigns element. Now 1 maps to 5, 1 maps to 5, 1 maps to 5, 2 maps to 7, 3 maps to 9, 4 maps to 11. Now, is this a function? Yes. Why? Because all the elements in the domain have images. 1 has an image of 5, 2 has an image of 7, 3 has an image of 9, 4 has an image of 11. Secondly, there's no element in the domain that has more than one image. Now, our solution set that I defined earlier, for those of you that may not even understand what I did or what I said yet, the solution set in this case is the set that contains 1, 5, 2, 7, 3, 9, and 4, 11. So this is our solution set, and this is as simple as ABC. Then another set that you should note here is the set of the domain. So the domain set contains 1, 2, 3, and 4. And now the codomain set is B itself, and the codomain is 5, 7, 9, 11, and 13. Now there's also what we call the range, the set of range. Now the set of range is defined on R. You can write it as R. Now the range is the set of elements in the codomain that have pre-image. So 5 has a pre-image of 1, 7 has a pre-image of 2, 9 has a pre-image of 3, 11 has a pre-image of 4, 13 does not have any pre-image. Now the range is 5, 7, 9, 11. And from what you can see, it is obvious, I said it earlier, that the range is a subset of the codomain. And that is all I've been saying. And I really hope you understand it. Now another example to make it much more easier for you to really understand. Another example, let's say you have a rule, and this time around the rule is let me use y being equal to x squared. Yeah, let's say this is the rule this time around, and I want you to observe a function that maps x to y, where x is an element of x and y is an element of y. Now from this definition, let's say we are picking from -1, 0, 1, and 2, and let's say the set of elements we have in the codomain are let's say we have -1, let's say we have 0, let's say we have 1, let's say we have 3, let's say we have 4. Yeah. Now from this rule, this particular rule, that's big. Now from this rule, we have that 1. If you subscribe 1 into this, I'm sorry, -1 into this, you subscribe -1 into this, the square of -1 is 1. So -1 maps to 1. Now the square of 0 is 0, so 0 maps to 0. The square of 1 is 1, so 1 maps to 1. The square of 2 is 4, so 2 maps to 4. Is this a function? Yes. Why? Because it satisfies the two conditions of a function. The first condition is that all the elements in the domain must have images, and the second condition is that no elements in the domain must have more than one image. Do you understand? And it satisfies the two. So what is our solution set? What's the solution set? I'm sure by now you know that the solution set is the set -1, 1, the set 0, 0, the set 1, 1, the set 2, 4. These are our solution sets. Now, if I ask you what is the domain set, the domain set is obviously the set -1, 0, 1, and 2, and the codomain set, which is y, is the set -1, 0, 1, 3, and 4, and the range. Now, another way to write the range is to write it as a function of x you understand? Function of x. That's another way to write it. And it is those elements in the codomain that have pre-images, or a set of those elements in the codomain that have pre-images. And they are 0, 1, and 4. 0, 1, and 4. Logically, if you look at the solution set, you see that it's only 0, 1, and 4 you have there. 1 is twice, which tells you that 1 has a pre-image, or that's 2 pre-image, which are -1 and 1. So that's the range, and that is all we have been defining since morning. And that tells you a lot about the concept of function. I've also given you the concept or the definition of the solution set. So now you know how to find your solution set. You know how to find your range. You know the meaning of domain and codomain. Now, note this. F is said to be a function. I need you to note this. F is said, or F is a function from A to B. F is a function from A to B if for any x and elements of A there exists unique y and elements of B such that y is equal to f of x is true, such that y is equal to f of x is true, such that y equal to f of x is true. So note that. Now let me quickly give you some logical examples. We've done quite a number of examples already, so let's do more. Now let's say I tell you that if I say let A be equal to 1, 2, 3, and 4, and B is equal to 1, 4, 9, and 16. Now, suppose a propositional function, P. Now, this is a new word, propositional function, and I'll explain, don't worry, just calm down. Propositional function P of x, y on A cross B is defined by y being equal to x squared, full stop. Investigate whether the relation f which is a comma b comma the propositional function is a function. So they want us to investigate whether a relation is a function. So is a function A from B, or is a function A is a function A from B, or is a function A to B. Do you understand? So investigate whether it's the function A to B. Now let us solve this question together. And I promised that I was going to tell you the meaning of propositional function. Now, when you say propositional function, you are simply just saying the rule that applies. And anytime you have the rule, there's always an input and an output. And it is the same thing we have been saying since the beginning of this class. Now, we have the first coordinate element and the second coordinate element. So by representing it as a propositional function, you are simply just saying, okay, a function that actually has first coordinate and second coordinate. So a very good example, look at this solution set that has -1. So if I write propositional function there, what am I trying to write? If I write propositional function of x and y like this, I'm simply trying to write a function that contains -1, 1, 0, 0, 1, 1, 2, 4. You understand? So I already told you, or I already wrote it as y being equal to x squared. And because y is equal to x squared, you know that y is equal to f of x. And because y equal to f of x, in a Cartesian system, you do know that for every x, there must be a y. Do you understand? For every x, there must be a y. So just writing it as propositional function. Simple as ABC. So that's the idea. The idea of propositional function is just, okay, for every input, there is an output. So by writing a relation like this, we are just trying to relate a domain, codomain with the other pairs of elements in them. Now, they want us to investigate whether this relation is a function A to B or not. So how do we do that investigation? And how do we know whether f is actually a function or not? We have two things to verify. The first is that are all elements in the domain are they mapping to one element, or are they mapping to elements in the codomain? Another way to put that, all the elements in the domain, do they have images? Then secondly, do they have one and only images each? So we need to verify those two statements. And as soon as we are done verifying the two statements, then we can be sure that it is a function. It is a function. Now, from what you know, our solution set F is actually defined on x and y like this, such that y is equal to x squared. You know, from the question, it told us that the propositional function is defined on y equal to x squared. And of course, x is an element of A, y is an element of B. X is an element of A, y is an element of B. Now, let us check what is happening here. The solution set F has an output of the Cartesian expression x and y, and a distinct property of any element x in set A, a distinct property of any element x in A, and element y in B that satisfies this should be in a particular list. So what am I saying? I'm saying that from what we have here, then anytime x is 1, anytime x is 1, you have y to be 1 as well. Also, anytime x is 2 and you subscribe 2 here, you have y to be 4. Anytime x is 3 and you subscribe 3 there, you have y to be 9. And anytime x is 4 and you subscribe 4 here, you have y to be 16. Now, this is our solution set, and this is exactly what we need. And because this particular relation follows the two rules, which is that each and every element here must have an image here, and no element, in no case do you have one appearing twice as first coordinate element. No element in the domain must have more than one image. So it satisfies the two. Then we observed that every element of A has an image in B. And also the second one, and that no element, and that no single element of A has two images. No element of A has two images in B. No element in A, or no single element in A of A has two images in B. And hence, F is a function. F is a function from A to B. is a function from A to B. Now, I'll give you a question or a practice question, and I need you to solve it yourself. All right, the question says, let A be a set of A, B, C, D, B a set 1, 2, 3, and the solution set F of the relation F of A, B and the propositional function X, Y be the set A, 2, C, 3, and D, 1. Investigate whether F is a function from A to B. So, I need you to pause the video and solve this question. Alright, welcome back. So let's solve the question. Let's solve the question. This is the domain and this is the codomain. And from these solution sets, we have that A has an image of 2. B is not even in the solution set, which means that B does not have an image. C has an image and D has an image. This actually fails the first rule, which states or tells us that all the elements in the domain must have an image. The second says that none of them is permitted to have more than one image. So because of this, it is obvious and you can tell that it is not a function. So you say because the element B in A or in set A does not have an image, then we conclude that F is not a function from A to B. Or you can just say because the element B in A does not have an image in B. Do you understand? To make it more balanced, in B, in set B. So it does not have an image in set B. In B, then we conclude that F is not a function from A to B. Now let's solve one more example, and I'll talk about a concept, and that's the concept of domain of a function. All right, the question says that let A, which is a set of 1, 4, 9, and B a set of -3, -2, -1, 1, 2, and 3, and P of X, Y being a propositional function defined by y squared to be equal x. Now show that the relation F of A, B, then the propositional function from A to B is not a function from A to B. So how do we show that this particular relation, the entire relation here, is not a function? How do we show that? Right. The first thing to do, or the first way to know, is to actually define what we call the solution set. So the solution set, which is set F of the relation is F, which is actually, now A is the domain and this is the codomain. Now when A is 1 or when X is 1, then the square of 1 is 1. So it means that 1 will actually map to 1. Also, if you check 1 again, you also observe from the set of elements in B, you notice there is -1 here. If you put -1 into this, you also observe that -1 is also true. So I'm saying that when x is 1, y can also be minus 1. It is true. Y can be minus 1. Anytime you write y squared is equal to x, is actually is the same thing as just writing y being equal to plus or minus the root of x. And by writing this, it means that when x is 1, it means that when x is 1 here, y can be plus or minus 1. Do you understand? So plus 1 applies, then minus 1 also applies anytime x is 1. In the same way, when x is 4, y can be plus 2, and at the same time, the same y can be minus 2. Or do you understand? So anytime x is 4, y is either 2 or minus 2. From this definition, if you put 4 here, y is the same thing as plus or minus 2. And also, anytime x is 9, y is either plus 3 or minus 3. This is our solution set from what they give us. Now, now, let me put this into a box. Now, one thing I want you to know or to know is that this is the case where one from domain A, you have a function, or sorry, a relation. So this is the case where one is mapping to two elements, which are minus 1 and 1. So 1 maps to minus 1, the same one maps to 1 to many. And that is not allowed in the entire concept of function. Also, 4 maps to minus 2 and plus 2. Do you understand? 4 maps to minus 2 and plus 2. Same with 9. And because of those blunders, a great negation of the idea and concept of function, then we can see that f is not a function. Do you understand? The relation f from A to B, the relation f from A to B is not a function. Do you understand? It is not a function because it has negated the second rule. Actually, the first rule is satisfied. Now the fact that each and every element in the domain have images, yes, but it fails the second rule. Do you understand? And if you observe that, or you notice that 1 and 1 and 1 and minus 1 are elements of the solution set, and from this we don't have that. It does not imply that 1 must give you minus 1. It is not. Do you understand? This is not the case. 1 is not minus 1, and because 1 is not minus 1, it fills the second rule, which I already said. Do you understand? So it means that an element of A has 2 images in set. Now this violates the definition of the function. Hence, so you just write concluding, this violates the definition. This violates the definition of a function. And f is not a function. F is not a function from A to B. From A to B. And that leads us to the definition or the concept of domain of a function.
And subjective. What did I say?